The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let me remind you, yesterday we've defined and started to compute line integrals for work of a vector field along a curve. Okay, so we have a curve in the plane, C. We have a vector field, F, that gives us a vector at every point. And we want to find the work done along the curve. So that's the line integral along C of f dot dr, or more geometrically, line integral along C of f dot t ds, where t is the unit tangent vector and ds is the arc length element. Or in coordinates, that's the integral of m dx plus n dy, where m and n are the components of a vector field. Okay? So let's do an example that will just summarize what we did yesterday, and then we'll move on to interesting observations about these things. So here's an example we're going to look at now. Let's say I give you the vector field yi plus xj. So it's not completely obvious what it looks like, but here's a computer plot of that vector field, so that tells you a bit what it does. Points in all sorts of directions. And let's say we want to find the work done by this vector field if I move along this closed curve. I start at the origin, then I moved along the x-axis to 1, then I move along the unit circle to the diagonal, and then I move back to the origin in a straight line. Okay, so C consists of 3 parts. So that you enclose a sector of a unit disk corresponding to angles between 0 and 45 degrees. So to compute this line integral, well, what we have to do is we have to set up 3 different integrals and add them together. Okay, so we need to set up the integral of y dx plus x dy for each of these pieces. So let's do the first one. On the x-axis, well, one way to parameterize that is to just use the x variable and say that because we are on the, we're going from the origin to 1, 0. Well, we know we're on the x-axis, so there's y there is actually just 0, and the variable will be x from 0 to 1. Or if you prefer, you can parameterize things, say x equals t for t from 0 to 1, and y equals 0. What doesn't change is y is 0, and therefore dy is also 0. So in fact, we're integrating y dx plus x dy, but that becomes, well, 0 dx plus 0, and that's just going to give you 0. Okay, so there's the line integral here is very easy to compute. Of course, you can also do it geometrically, because geometrically, you can see on the picture, along the x-axis, the vector field is pointing vertically. Right? If I'm on the x-axis, my vector field is actually in the y direction. So it's perpendicular to my curve, so the work done is going to be 0. F dot t will be 0. So f dot t is 0, so the integral is 0. Okay, any questions about this first part of the calculation? No? It's okay? Okay, let's move on to a more interesting part of it. Let's do the second part, which is a portion of a unit circle. Okay, so maybe I should have drawn my picture. And so now we are moving on this part of the curve, that's C2. And of course, we have to choose how to express x and y in terms of a single variable. Well, most likely, when you're moving on a circle, you're going to use the angle along the circle to tell you where you are. Okay, so we're going to use the angle theta as parameter, and we'll say, well, we're on the unit circle, so x is cosine theta, and y is sine theta. What's the range of theta? Theta goes from 0 to pi over 4. Okay? So whenever I see dx, I will replace it by, well, the derivative of cosine is negative sine, so minus sine theta d theta. And dy, the derivative of sine is cosine, so it will become cosine theta d theta. Okay, so I'm computing the integral of y dx plus x dy. That means I'll be actually computing the integral of, so y is sine theta, dx, that's negative sine theta d theta, plus x is cosine, dy is cosine theta d theta, from 0 to pi over 4. Okay, so that's integral from 0 to pi over 4 of cosine square minus sine square. And if you know your trig, then you should recognize this as cosine of 2 theta. Okay, so that will integrate to 1/2 of sine 2 theta from 0 to pi over 4, sorry. And sine pi over 2 is 1, so you will get 1/2. Okay, any questions about this one? No? Okay, then let's do the third one. So the third guy is when we come back to the origin along the diagonal. Okay, so we go in a straight line from this point. Where's this point? Well, this point is 1 over root 2, 1 over root 2. And we go back to the origin. Okay, so we need to figure out a way to express x and y in terms of the same parameter. So one way, which is very natural, would be to just say, well, let's say we move from here to here over time. And, you know, at time 0 we're here, at time 1 we're here. We know how to parameterize this line. So what we could do is say, let's parameterize this line. So we start at 1 over root 2, and we go down by 1 over root 2 in time 1, and same with y. That's actually perfectly fine, but that's unnecessarily complicated. Okay? Why is it complicated? Because we'll get, all of these expressions. Would be easier to actually just look at motion in this direction and then say, well, if we have a certain work, if we move from here to here, then the work done moving from here to here is just going to be the opposite. Okay? So in fact, we can do slightly better by just saying, well, we'll take x equals t, y equals t, t from 0 to 1 over root 2, and take, well, sorry. That gives us what I will call minus C3, which means C3 backwards. And then we can say the integral for work along minus C3 is the opposite of the work along C3. Or, if you're comfortable with integration where variables go down, then you could also say that t just goes from 1 over square root of 2 down to 0. And when you set up your integral, it will go from 1 over root 2 to 0. And of course, that will be the negative of the 1 from 0 to 1 over root 2. So it's the same thing. Okay, so if we do it with this parameterization, we'll get that, well, of course, dx is dt, dy is dt. So the integral along minus C3 of y dx plus x dy is just the integral from 0 to 1 over root 2 of t dt plus t dt. Sorry, I'm messing up my blackboard. Okay. Which is going to be, well, the integral of 2t dt, which is t squared between these bounds, which is 1/2. That's the integral along minus C3, along the reversed path. And if I want to do it along C3 instead, then I just take the negative. Okay? Or if you prefer, you could have done it directly with integral from 1 over root 2 to 0, which gave you immediately the negative 1/2. Okay, so at the end, we get that the total work was the sum of the 3 line integrals. I'm not writing f.dr just to save space. That's 0 plus 1/2 minus 1/2, and that comes out to 0. So a lot of calculations for nothing. Okay, so that should give you a good overview of, various ways to compute line integrals. Any questions about all that? No? Okay. So next, let me tell you about how to avoid computing line integrals. Well, one is easy. Don't take this class, but that's not. So here's another way not to do it. Okay? So let's look a little bit about one kind of vector field that actually we've encountered a few weeks ago without saying it. So we said when we have a function of 2 variables, we have the gradient vector. Well, at the time it was just a vector, but that vector depended on x and y. So in fact, it's a vector field. Okay? So here's an interesting special case. Say that f, our vector field, is actually the gradient of some function. So it's a gradient field. And So f is a function of two variables, x and y, and that's called the potential for the vector field. The reason is, of course, from physics. You know, in physics, you call potential, well, electrical potential or gravitational potential, or potential energy, this function of position that tells you how much actually energy is stored somehow by the force field, and its gradient gives you the force. Actually, not quite. If you're a physicist, then the force will be negative the gradient. So that means that physicists' potentials are the opposite of the mathematician's potential. Okay, so that's just here to confuse you. It doesn't really matter, but so to make things simpler, we are using this convention, and you just put a minus sign if you're doing physics. So then I claim we can simplify the evaluation of the line integral for work. Okay? So perhaps you've seen in physics the work done by, say, the electrical force is actually given by the change in value of a potential from the starting point to the ending point. Or same for gravitational force. So these are special cases of what's called the fundamental theorem of calculus for line integrals. So the fundamental theorem of calculus, not for line integrals, tells you if you integrate a derivative, then you get back the function. And here it's the same thing in multivariable calculus. It tells you if you take the line integral of the gradient of a function, what you get back is the function. Okay, so the fundamental theorem of calculus for line integrals says the following thing. It says if you integrate a vector field that's the gradient of a function along a curve, let's say that you have a curve that goes from some starting point, P0, to some ending point, P1, then all you will get is the value of f at P1 minus the value of f at P0. Okay? So that's a pretty nifty formula, but it only works if the field that you're integrating is a gradient. You know it's a gradient, and you know the function little f. I mean, we can't put just any vector field in here. We have to put the gradient of f. So actually, on Tuesday, we'll see how to decide whether a vector field is a gradient or not, and if it is a gradient, how to find the potential function. So we'll cover that. But for now, we're going to try to figure out a bit more about this, what it says, what it means physically, how to think about it geometrically, and so on. So maybe I should say, if you try to write this in coordinates, because that's also a useful way to think about it, if I give you the line integral along C, so the gradient field, the components are f sub x and f sub y. So it means I'm actually integrating f sub x dx plus f sub y dy. Or if you prefer, that's the same thing as actually integrating df. So I'm integrating the differential of a function f. Well, then that's the change in f. And of course, if you write it in this form, then probably it's quite obvious to you that this should be true. I mean, in this form, actually, it's the same statement as in single variable calculus. Okay? And actually, that's how we prove the theorem. So let's prove this theorem. How do we prove it? Well, let's say I give you a curve, and I ask you to compute this integral. How will you do that? Well, the way you compute the integral actually is by choosing a parameter and expressing everything in terms of that parameter. Okay, so we'll set, well, so we know it's f sub x dx plus f sub y dy. And we'll want to parameterize c in the form x equals x of t, y equals y of t. So if we do that, then dx becomes x prime of t dt, dy becomes y prime of t dt. So we know x is x of t. That tells us dx is x prime of t dt. Y is y of t gives us dy is y prime of t dt. So now what we are integrating actually is becomes the integral of f sub x times dx dt plus f sub y times dy dt times dt. Okay? But now, here I recognize a familiar guy. I've seen this one before in the chain rule. Okay? This guy, by the chain rule, is the rate of change of f if I take x and y to be functions of t, and I plug those into f. So in fact, what I'm integrating is df dt when I think of f as a function of t by just plugging x and y as functions of t. dt. And so maybe actually I should now say, I have sometimes t goes from some initial time, let's say t0 to t1, and now by the usual fundamental theorem of calculus, I know that this will be just the change in the value of f between t0 and t1. Okay. So integral from t0 to t1 of df dt, well, that becomes f between t0 and t1. F of what? We just have to be a little bit careful here. Well, it's not quite f of t. It's f seen as a function of t by putting x of t and y of t into it. So let me write that down carefully. What I'm integrating to is f of x of t and y of t. Right? Does that sound fair? Yeah. Okay. And so when I plug in t1, I get the point where I am at time t1. That's the end point of my curve. When I plug t0, I will get the starting point of my curve, p0. And that's the end of the proof. It wasn't that hard, see? Okay? So let's see an example. Well, let's look at that example again. Okay, so we have this curve, we had this vector field. Could it be that, by accident, that vector field was a gradient field? So remember, our vector field was y, comma x. Can we think of a function whose derivative with respect to x is y, and derivative with respect to y is x? Yeah, x times y sounds like a good candidate, where f of xy is xy. Okay? So that means that the line integrals that we computed along these things can be just evaluated from just finding out the values of f at the endpoint. So here's version 2 of my plot, where I've added the contour plot of the function xy on top of the vector field. Actually, see how the vector field is still pointing perpendicular to the level curves as we have seen, just to remind you. And so now, when we move, well, the origin is on the level curve f equals 0. And when we start going along C1, we stay on f equals 0. So there's no work. The potential doesn't change. Then on C2, the potential increases from 0 to 1/2. The work is 1/2. And then on C3, we go back down from 1/2 to 0. The work is negative 1/2. See, that was much easier than computing. So for example, the integral along C2 is actually just, so C2 goes from 1, 0 to 1 over root 2, 1 over root 2. So that's 1/2 minus 0, and that's 1/2. Okay, because C2 was going here, and at this point, f is 0. At that point, f is 1/2. And similarly for the others. And of course, when you sum, you get 0, because the total change in f, when you go from here to here to here to here, eventually you're back at the same place, so f hasn't changed. Okay, so that's a neat trick, and it's important conceptually because a lot of forces are gradients of potentials. I mean, namely gravitational force, electric force. The problem is not every vector field is a gradient. A lot of vector fields are not gradients. For example, magnetic fields certainly are not gradients. So a big warning. Everything today only applies if f is a gradient field. Okay? It's not true otherwise. Okay, still, let's see what are the consequences of a fundamental theorem. So, just to put one more time this disclaimer, if f is a gradient field, then what do we have? Well, there's various nice features of work done by gradient fields that are not true for other vector fields. So one of them is this property of path independence. Okay, so the claim is if I have a line integral to compute, then it doesn't matter which path I take as long as it goes from point A to point B. It just depends on the point where I start, the point where I end. And that's certainly false in general, but for a gradient field, it works. Okay, so if I have a point P0, a point P1, and I have two different paths that go there, say C1 and C2, so they go from the same point to the same point, but in different ways, then in this situation, the line integral along C1 is equal to the line integral along C2. Well, actually, let me insist that this is only for gradient fields by putting gradient f in here. Just so you know, you don't get tempted to ever use this for a field that's not a gradient field. If C1 and C2 have the same start and end points. Okay, how do we prove that? Well, it's very easy. We just use the fundamental theorem. It tells us if you compute the line integral along C1, it's just f at this point minus f at this point. If you do it for C2, well, same. So they're the same. Okay. And for that, you don't actually even need to know what little f is. You know in advance that it's going to be the same. So if I give you a vector field and I tell you it's the gradient of a mysterious function, but I don't tell you what the function is and you don't want to find out, you can still use path independence, but only if you know that it's a gradient. Oh. Okay. Okay, I guess this one is dead. So that will stay here forever because nobody's tall enough to erase it now. When you come back next year and you still see that formula, you'll see. Okay. Yes, but there's no useful information here. I mean, that's a good point. Okay. So what's another consequence? One, so if you have a gradient field, it's what's called conservative. Okay, so what's a conservative field? Well, the word conservative comes from the idea in physics, it's the notion of conservation of energy. It tells you that you cannot get energy for free out of your force field. So what it means is, in particular, if you take a closed trajectory, so a trajectory that goes from some point back to the same point. So if C is a closed curve, then the work done along C is 0. Okay, that's the definition of what it means to be conservative. If I take any closed curve, the work will always be 0. The contrary, not conservative means somewhere there is a curve along which the work is not 0. If you find a curve where the work is 0, that's not enough to say it's conservative. You have to show that no matter what curve I give you, if it's a closed curve, it will always be 0. So what that means concretely is, if you have a force field that's conservative, then you cannot build somehow some, perpetual motion out of it. You can't build something that will just keep going, just powered by that force, because that force is actually not providing any energy. After you've gone, one loop around, nothing's happened from the point of view of the energy provided by that force. There's no work coming from the force. While if you have a force field that's not conservative, then you can try to actually maybe find a loop where the work will be positive, and then that thing will just keep running. So actually, if you look at magnetic fields and transformers or power adapters and things like that, you extract energy from a magnetic field. Of course, I mean, you actually have to take some power supply to maintain the magnetic field. But so a magnetic field, you could actually try to get energy from it almost for free. A gravitational field or an electric field, you can't. Okay, so, and now why does that hold? Well, if I have a gradient field, then if I try to compute this line integral, I know that it will be the value of a function at the end point minus the value at the starting point. But they're the same, so the value is the same. So if I have a gradient field and I do the line integral, then I will get f at the end point minus f at the starting point. But they're the same point, so that's 0. Okay. So just to reinforce my warning that not every field is a gradient field, let's look again at our favorite vector field from yesterday. So our favorite vector field yesterday was negative y and x. It's a vector field that just rotates around the origin counterclockwise. Okay. Well, we said if you take, say you take just the unit circle, for example, counterclockwise. Well, remember we said yesterday that the line integral of f dot dr, or maybe I should say f dot tds now, so because the vector field is tangent to the circle, so on the unit circle, f is tangent to the curve, and so f dot t is length f times, well, length t, but t is a unit vector, so it's length f, and the length of f on the unit circle was just 1. So that's the integral of 1 ds, so that's just the length of the circle, that's 2 pi, and 2 pi is definitely not 0. So this vector field is not conservative. And so now we know actually it's not the gradient of anything. Because if it were a gradient, then it would be conservative, and it's not. So tells you, it's an example of a vector field that is not conservative. It's not path independent either, by the way, because see, if I go from here to here along the upper half circle or along the lower half circle, in one case I will get pi, in the other case I will get negative pi. I don't get the same answer. And so on and so on. It just, fails to have all of these properties. So maybe I will write that down. It's not conservative. Not path independent. It's not a gradient. It doesn't have any of these properties. Okay, any questions? Yes? How do you determine whether something is a gradient or not? Well, that's what we will see on Tuesday. Yes? Is it possible that it's conservative and not path independent, or vice versa? The answer is no. These two properties are equivalent, and we're going to see that right now. At least that's the plan. Yes?
So if it's not conservative, then it's impossible to draw level curves that are perpendicular to the different points?
Let's see. So you said if it's not path independent, then we cannot draw level curves that are perpendicular to it at every point. I wouldn't necessarily go that far. You might be able to draw curves that are perpendicular to it, but they won't be the level curves of a function for which this is the gradient. I mean, you might still have, if you take this gradient field and, scale it, but in strange ways, multiply it by 2 in some places, by 1 in other places, by 5 in some other places, you will get something that won't be conservative anymore. And it will still be perpendicular to the curves. So it's more subtle than that. But certainly, if it's not conservative, then it's not a gradient, and you cannot do what we said. And how to decide whether it is or not, that will be Tuesday's topic. So for now, I just want to figure out again, actually, let's now state all these properties. Oh. Actually, let me first do 1 minute of physics. So let me just tell you again, what's the physics in here. So if a force field is the gradient of a potential so I'll still keep my plus sign. So maybe I should say this is minus physics. But so the work of F is the change in value of potential from one endpoint to the other endpoint. And so, you might know about gravitational field or electrical field versus gravitational or electrical potential. And in case you haven't done, any 802 yet, electrical potential is also commonly known as voltage. Okay? It's the one that makes it hurt when you stick your fingers into the socket. Don't try. Okay, and so now conservativeness means no energy can be extracted for free from the field you can't just have a particle moving in that field and going on indefinitely faster and faster, or if there's actually friction, then keep moving. So total energy is conserved. And I guess that's why we call that conservative. Okay. Okay, so let's end with a recap of various equivalent properties. Okay, so the first property that I will have for a vector field is that it's conservative. So to say that a vector field is conservative means that the line integral is 0 along any closed curve. C. Maybe to clarify, sorry. Along all closed curves. Okay? Every closed curve that you give me any closed curve, I get 0. So now I claim this is the same thing as a second property, which is that the line integral of f is path independent. Okay, so that means if I have two paths with the same endpoints, then I will get always the same answer. Why is that equivalent? Well, let's say that I'm path independent. If I'm path independent, then if I take a closed curve, well, it has the same endpoints as just the curve that doesn't move at all. So path independence tells me instead of going all around, I could just stay where I am, and then the work would be just 0. So if I'm path independent, then I'm conservative. Conversely, let's say that I'm just conservative, and I want to check path independence. Well, so I have 2 points, and I have 2 paths between them. I want to show that the work is the same. Well, how do I do that? Oops, C1 and C2. Well, I observe that if I do C1 minus C2, I get a closed path. Right? If I go first from here to here and then back along that one, I get a closed path. So if I'm conservative, I should get 0. But if I get 0 on C1 minus C2, it means that the work on C1 and the work on C2 are the same. See, so it's the same. It's just a different way to think about the situation. More things that are equivalent. I have 2 more things to say. The third one, it's equivalent to f being a gradient field. Okay, so this is equivalent to the third property, f is a gradient field. Why? Well, if we know that it's a gradient field, then we've seen that we get these properties out of a fundamental theorem. Question is, if I have a conservative or path-independent vector field, why is it the gradient of something? Okay, so this way is the fundamental theorem. That way, well, so that actually, let me just say, that will be how we find the potential. So how do we find potential? Well, let's say that I know the value of my potential here. Actually, I get to choose what it is. Remember, in physics, the potential is defined up to adding or subtracting a constant. What matters is only the change in potential. So let's say I know my potential here, and I want to know my potential here. What do? Well, I take my favorite particle, and I move it from here to here, and I look at the work done. And that tells me how much the potential has changed. So that tells me what the potential should be here. And this does not depend on my choice of path because I've assumed that I'm path independent. So that's what we will do on Tuesday. And let me just state a fourth property that's the same. So all that stuff is the same as also 4. If I look at m dx plus n dy, is what's called an exact differential. So what that means, an exact differential means it can be put in the form df for some function f. And I'm just reformulating this thing, right? Because I'm saying just I can put it in the form f sub x dx plus f sub y dy, which means my vector field was a gradient field. So these things are really the same. Okay, so after the weekend on Tuesday, we'll actually figure out how to decide whether these things hold or not and how to find the potential.